thank you for your continued support of the Safety R&D webinar series through its first two series. The first being the available data resources with topics that were selected by popular vote by the safety field, and that was followed by the second series, SHARP 2 and its emerging uses. This third series is going to focus on development and use of analysis and modeling tools, applying available and emerging data sources. Today, Dr. Forrest Council of the University of North Carolina Highway Safety Research Center will speak to us about a concept that has been under development thanks to the support of the Exploratory Advanced Research Program and performed under the Highway Safety Information System Program. He has been working with Drs. Harkey, Srinivasan, and Lan. The HSIS program has dedicated most of the past 2 years to the artificial realistic database with its kickoff on the 21st of August of 2015. ARD is a synthetic database. It represents actual data sets, but it allows for analyses of topics with limited data. This is expected to serve as a modeling test bed as well as to provide a more even playing field for future HSIS data contest entrants. Dr. Council will discuss the development of this important tool and provide context to its current and future relevance. We will ask you to hold your questions to the end or make use of the chat pod to issue any questions or comments at any time. With that, I'm going to pass the floor to Forrest Council. Thank you.
Thank you, Anna Maria. As you can see, Anna Maria said this, I'll just repeat it. We had two sponsors, even though you'll be seeing the HSIS logo on all the slides, the HSIS program, but also the Exploratory FSWA, Exploratory Advanced Research Program. Okay, here's what we're going to be covering today. We'll do an introduction. I'll do an introduction or a little bit about background and concept, some of the past tasks that were done before the current project, the three major components, which are a roadway generator, a crash generator, and a model grading procedure, something about the limited pilot testing we're doing now, the deliverables to FHWA, possible future ARD efforts, and then at the end, an introduction to the study team who will be helping answer all the questions that come up. We're having a little bit of technical difficulty. You have to excuse us. Okay. There's a number of reasons for getting into the development of ARD, artificial realistic data, but let me give you the one that I think was the primary reason for starting on this. We're talking about crash modification factors or crash modification functions, which are very important roadway safety programs because they're used in determining whether or not to apply a given treatment to a given segment or location. I think most of you probably already know what CMFs are, but I'll give this is just a quick primer. A CMF, crash modification factor, is a multiplicative factor used to compute the expected number of crashes after you implement a given countermeasure at a specific site. So it's a pretty simple concept. If the CMF for a given treatment is 0.8 and you expected 100 crashes at the site without the treatment, then you multiply the two and you would expect 80 crashes at the site with the treatment. The problem, there's general agreement, here's why we got into ARD. There's general agreement that well-designed before-after studies provide reliable crash modification factors. And the reason for that is when you do a before-after study, something actually got changed out in the real world. You actually implemented a treatment, you made a change, and now you're going to study what happened. It's not simply before and after, but basically in a before-after context. You can't always do before-after programs, though, for some of the roadway descriptors. Median width, for example, will usually not change by itself. You don't go out and change a median width without changing other things like adding lanes, changing shoulder width, or changing lane width. So in these cases, we have to use what are referred to as cross-sectional methods. We combine roadway sections that have lots of different characteristics, so different median widths, for example, but nothing really is modified. We didn't go out there and change a median width by itself. The most common cross-sectional methods are regression models, and they look something like the one that's shown on the slide. And what we know about these is that if you do a good model, if you build a good model, it'll predict the outcome, that is, number of crashes or number of crashes within severity categories very well. If it fits the data, it does a good job of predicting why. And there's lots of statistical measurements that tell you how well a model fits the data and predicts why. The question we have, though, is can we use those individual coefficients like the B3 for median width? Once we figure out what that is in the modeling, is that a good measure of a crash modification factor for median width? And unfortunately, the answer is probably or maybe or probably not. The thing is, we don't know how good B3 is as a crash modification factor. We have no knowledge of underlying truth, so we have no truth to compare to. So what we do then is we've developed this ARD. That's the solution, the artificial realistic data. We built a data set where the underlying true relationships are known. That is, we built them into the data set. We defined what they are, and then we built them into the data set. We keep these relationships secret. We don't give the users the answers, so the users don't know it. They have to get their answers for what truth is based on their model or their cross-sectional analysis technique. We build in randomness and confounders. The researchers take the data and apply their cross-sectional methods using the data set. They submit them to the ARD administrator to be graded. And then the grading determines how well the method they use captures this underlying truth that we built into ARD. And what we're looking at is which models which methods that they're using are ultimately better at doing this than other methods. So the overall goal is to improve this cross-sectional method so that more reliable CMFs can be obtained. In this sense, the ARD is a tool. It's a database, but it's a tool that when used by analysts will help us reach the goal of developing better CMFs. I'm going to say it in a little different way on this disclaimer slide. What you cannot do with ARD is you can't go into the database and learn new information about how safety is affected by a roadway characteristic. You can't do that because we built in those answers instead of letting them come from some type of real-world data set. ARD is a tool which can be used to determine which procedures best define that relationship. So if I'm looking for a relationship for effective crash frequency of increasing lane width, what I'm finding with ARD is which procedures do a better job of defining the effect on crash risk of lane width. And then using these cross-sectional procedures will then lead to better knowledge about the relationships that we're trying to build. So by using the better procedures, we learn better information. Past tasks, very briefly, ARD has been limited, or this version, to non-intersection crash predictions on two-lane rural road segments. We did, as part of the HSIS project more than 2 years ago, developed a plan for developing a roadway network generator and a plan for developing the secret crash predictions based on these inventory data. Excuse me. The roadway generator, here are the three major components. The roadway generator generates homogeneous segments, very short segments, 0.02 of a mile long, with realistic characteristics. The crash generator then takes embedded causal rules that define the true relationships, the crash generator has taken and has embedded these rules which will define crashes, defining the relationship between roadway descriptors and crash frequency or severity. And then we have a computerized system to put the two of these together. It generates the roadway file, attaches the crash counts to each segment, and then sends the combined file to the user. The method grading procedure then would, after the user sends results back in, would determine how well the results capture the embedded true relationships. And then we're doing a limited pilot test to see if it works, if the computerized ARD system can be computerized, and if common statistical approaches can be developed and graded. Okay, the roadway generator as it stands today is 2,400 miles of 0.02 mile, each segment 0.02 of a mile long. You can put this, the user can then join segments together to make longer homogeneous segments. It's primarily based on data from the Washington DOT HSIS inventory system, but we also, the developers used additional data from other sources that are listed on the slide, including US RAP, Google Earth, the Green Book, weather data from NOAA, and the Highway Capacity Manual. The roadway generator assigns a characteristic in ARD, which is often based on something called a Markov chain principle. And I'll get a little bit technical, although I can't get too technical on this. Basically, the Markov chain principle is that the descriptor value, or for one descriptor for an 0.2 mile segment is a function of that value on the previous segment. There's some high probability. For example, shoulder width on a given segment, if we're trying to assign a shoulder width, there's some high probability of it being the same as on the preceding segment and some lower probability that it will change. So in the development, the roadway generator developed and incorporated Markov chain, quote, transition tables that determine these probabilities of a descriptor either staying the same or changing on the next segment. The bottom line here is that a realistic set of characteristics is being generated for each segment. These are the elements. Some of these are groups of elements, but these are the elements that are generated for each of the inventory segments. The ones in red are ones that you would see sometimes in a normal HSIS type inventory database. Sometimes you don't see all of these. For example, not many states really have vertical alignment or horizontal alignment built into their inventory. Very few, if any, state systems would have these other things: land use classes, hourly flows by vehicle type, road user factors, winter maintenance factors, average traffic speed by time of day. So there's a lot of these factors for each segment that have to be there. We had to generate these because the causal rules require knowing what they are to predict a crash. So think of the blue ones as being non-normal things, the red ones as being normal, but all of these are required by the different causal rules. The crash generator itself was developed by Dr. Ezra Hauer, working with through 12 working papers. It estimates excuse me, crashes for 4 basic crash types on these 2-lane rural roads. What we call genuine single vehicle, those are drift from lane crashes. Then there's 3 types of single vehicle crashes that are preceded by a multi-vehicle conflict, like a vehicle being slow or stopped in the lane ahead of you and the trace vehicle having to avoid that vehicle slowing down, and that could ultimately become a single vehicle crash. That's one of the 3 types. Multi-vehicle, the third major type is the multi-vehicle same direction crashes like rear-end crashes, and then the multi-vehicle opposite direction crashes like head-on. So each crash type is then estimated for 3 vehicle types and for 5 severity classes. So there's lots of estimates here. The randomness in the crashes per segment generated is built in for each user's data. How are the crash types generated? For each type, a set of causal rules was defined specifying how each descriptor, each roadway descriptor, would affect a given crash type. For example, how would driveway count affect the probability of a genuine single vehicle crash? So there's a causal rule defining how that, what that relationship is. These rules produce factors or mathematical expressions. The factors are multiplied together and by flow to produce estimates of average expected crashes given the combination of roadway factors. And two things to remember so far: these estimates are not yet similar to estimates based on real-world reported crashes. They're not in the same ballpark yet. We haven't scaled them. And these estimates are for total crashes, both reported and unreported. And remember that in real-world crash databases, all we have to work with are the reported crashes. We don't have unreported ones. So we're trying to convert these estimates of average expected crashes based on the rules and factors into reported crashes on a segment, because that's what researchers really get to work with. This is to be realistic. The rule factor-based estimates are scaled to be similar, kind of in the same ballpark, with average total crashes that we would see in real-world crash databases if all crashes were reported. And then the scaled total crash estimates are converted to crash counts for each segment, assuming a Poisson distribution. And then the counts for each segment are adjusted to take into account how often crashes or what proportion of the time crashes get reported in each severity class. So as you can tell, it's not very simple. The example of the crash generation, let's talk a minute about genuine drift from lane single vehicle crashes. This is, our estimate is about 75% of the total single vehicle crashes will be this type in the real world. This drift from lane crash or genuine single vehicle crash is estimated using two sets of causal rules. One set affects the probability of drifting from the lane, and the second set of rules, complete set of rules, affects the probability of not recovering and thus becoming involved in a single vehicle crash. This is one rule example. One rule that affects the probability that a vehicle drifts from lane, which remember was one of our two factors in the last slide, relates to the number of driveways. It's hypothesized in the system, built into the system as a rule that assumes that the more driveways, the lesser the driver's inattention and drowsiness. So the more alert the driver is. And if the driver's more alert, then that lowers the probability of drifting from the lane. If you look at the chart, you can see it doesn't affect it much. It don't 2 or 3%. The one only for 0 driveways only drops down to 0.98 for 4 driveways a segment. So it's not a big effect, but it's an effect, and it's built into the system. So this driveway-related rule is one of 17 that's embedded in the ARD for to predict the probability of a vehicle leaving its lane. And then there's a total another set of causal rules related to the probability of not recovering. Second example, this is the one that has to do with conflict-related crashes. And if you kind of just look up the axis going up from the left up toward the top, a conflict occurs, either a collision avoidance maneuver is executed or not. It's either successful or not in box D, and then in box F, if it's successful, the driver either recovers or does not recover. And if he does not recover, then it becomes a single vehicle crash. So there's a different set of causal rules for each of those boxes, the A, B, D, F boxes that I just described. The bottom part of this slide talks more about multi-vehicle crashes and how they're generated, but we won't get into that. In summary, the ARD is a very complex system, but it's based on realistic assumptions. It's basically based on the best we know of in terms of causal rules. The method grading procedure that we're working on will compare the results from the analysis that a user sends us, their results. They built the safety relationships, and we compare those with the safety relationships that were input into the system. There will be a series of plots done to make the comparison. At least that's what we're working on now, and the degree of success would be judged by summary statistics such as bias or variance. Thanks. We're doing a limited pilot test right now in which one experienced modeler who's actually a member of the HSIS team but had nothing to do with developing ARD, so they don't know the secret relationships. They're going to use the 2,400 miles of data to develop regression models or another type of cross-sectional analysis technique, another technique that relates genuine single vehicle crashes to roadway characteristics. Their goal is to develop crash modification factors or functions for lane and shoulder width. So those are the two they're going to concentrate on. They're being asked to build at least one model which would use those limited to those items, those roadway descriptors that are normally seen in state databases. So basically the red ones in the slide, the red colored ones in the slide you saw earlier. And then the model results will be graded. Deliverables to FHWA. The project ends at the end of the current HSIS project, the end of this month. The deliverables will include the finalized inventory data set of 2,400 miles of 200th of a mile segments, rural two-lane roads, each segment described by 54 variables, some of which are for each direction and each hour of the day, like speed and traffic flow. There will be SAS code for the generation of the roadway inventory data set, and this will allow us, with not a lot of change in whoever it's administering our ARD in the future, to expand the mileage. We could generate more than 2,400 miles by some relatively simple changes in the SAS code at this point. The deliverable will also include the conceptual, causal rule, and scaling methods for all 6 of the crash types that I noted earlier. Those will be documented in the final report and in the 12 working papers. The 12 working papers will be submitted to FHWA, but they won't be published because that would give out the answers that we're having people look for. There also a deliverable is the SAS code for the generation of the genuine single vehicle crash count, so the drift from lane events based on the inventory variables. That's the first set we've completed the SAS. That's the set we completed the SAS code on. And we're going to see what we can learn from those before proceeding any further. And then initial results and recommendations from the pilot test modeling effort. Future efforts. So after that, there may well be work done, additional work done on the ARD, Artificial Realistic Data System, in the 18-month ongoing effort or new effort for the Highway Safety Information System. FHWA put out a RFP, and there's going to be 18 months of Highway Safety Information System work done starting in June. And there may be part of that related to the ARD. So that's why these are coded as possible future efforts. You could do for certain additional pilot testing using genuine single vehicle crashes only. So get more than one user, get a number of users, recruiting both experienced and less experienced, and then try to see if we indeed can learn which statistical approach is best or approaches are best. So if we have a number of different approaches tried and we grade those approaches, then we can see if we can learn which approaches are best. And again, these are all cross-sectional analysis type approaches. You could, or in the future, the SAS coding could be completed for the remaining 5 crash types, all the causal rules for the remaining 5 crash types. We would suggest if the additional testing, if the testing on the single vehicle crashes above is successful, so it's kind of a step-by-step procedure. You could do additional modeling with these other crash types once they're coded, and then you could combine all of these into published all the results, the grading results, into published information on best cross-sectional procedures or best modeling practices, basically. And then way down the road, even further, you could expand ARD into other crash types at different locations, like angle crashes at intersections. Or you could, way down the road, start from scratch and develop a conceptually new ARD for before-after study design. So figuring out which before-after study designs are the best. Next slide. Okay, here's the project team that put this together. Srini and I were co-PIs on this task within HSIS. Dr. Ezra Howrah, who some of you know, I'm sure, from the University of Toronto, retired, was in charge of developing the safety relationships and all the working papers. Doug Harwood for MRI Global headed up the development of the inventory database and the SAS coding for generating that. Dr. Bo Land from our staff here at HSRC is our SAS database developer. She's the one that had to take all of those 12 working papers and interpret what Dr. Howard was saying, and then rewrite them in SAS code so that the system is computerized. Anu Nujeti, who's our HSIS lab manager up in DC, provided data support. And we're back early in the process. Yusuf Muhammad Shah, who's now with the Sharp 2 program up there with FHWA, also provided some of the initial data. And then David Harkey, who's the director here, set in probably more than he wanted to meetings to provide technical inputs on all of the ARD process. And then finally, we're ready for questions. Next
one. We have the opportunity to either ask questions via the telephone line, or we have some that I've seen have accumulated through the chat pod. Caroline?
Yes.
If you would like to give instruction on how to unmute the phone, because many may have logged in without the access code.
Sure. Folks, if you need an access code, if you can tell us in the chat box, we can send you those directions. We'll actually do that to you now. I was pulling up the chat to see what the question was. So this is from George Merritt. When you say do a better job, how do you assess what is doing a better job?
Basically, that's what the grading procedure will do. So the grading procedure for each approach that's used by a modeler, and the modeler sends in his results, and we're going to compare those results to the truth that we've embedded into the system. So if that person, for example, was trying to do a CMF for driveway count, then we would see how well their CMF for driveway count reflects what we had built into the system for driveway count. So that's the basic procedure. I'll let any of my other colleagues add to that.
No, I think that's a good answer.
Okay, and another question, does the built-in truth in ARD potentially bias how different cross-sectional evaluations are graded?
Wow.
Not that we know of.
Yeah, not that we know of. As we've said, what we basically have is truth that we've built in, and then the user is using our database to try to get at that truth. So we think there won't be any potential bias caused by using different cross-sectional procedures.
Well, this is Carl. If I can expand on my question. If you build in truth, then you're building in a relationship between some sort of an action you might take, some sort of a countermeasure, and its result. And so what I'm looking at is, if that isn't really the way it happens in the real world, do you wind up with cross-sectional analyses that are reflective of what the relationships you've designed rather than of the real truth, rather than the ARD truth? I'm not sure that I'm getting this across correctly. I'm just not sure how the cross-sectional analyses grading might be skewed to the relationships that the ARD is establishing.
That's a good question, Carl. Yeah, what you're saying is if somebody comes up, I think what you're saying is somebody comes up with a good procedure that defines truth as we have defined it, can we also assume that that same procedure will define truth in the real world? And I think the answer to that is that's one of the things we thought about, and our assumption is yes, it'll work that way. If you have a procedure that does a good job with the realistic data that we're trying to produce here. You know, we're trying to produce data that's as realistic as possible in terms of inventory data, and then we have to guess what the causal relationships are. We think it'll be transferable. So if you have a good procedure here, we're certainly hoping that that procedure would be good with the data that you find in the real world. If it doesn't work that way, we're not sure where you go from here, because you never in the real world are going to know what the underlying truth is, so you're not going to be able to tell how well your procedure defined it. So, you know, our initial conceptualization of this was that yes, it would carry over, it would transfer.
Forrest, this is Monique. I have a question for you. Does it matter how much truth you have in the ARD? For instance, with the example you gave, you based it on driveway spacing. Say, for instance, you knew the width of the clear zone, or the number of obstacles within the clear zone, or some other thing that could potentially be relevant. If you populated the ARD with that in addition to the driveway information, do you get a better outcome, a more realistic outcome?
In the sense, I think I'm going to answer this right, but I'm looking at the other two to be sure I'm right. You know, these things are in the way we've designed this. You have to limit your factors at some point, but basically Dr. Howard tried to think of, you know, as many factors as he could think of that would affect each of the causal, you know, build causal rules for as many as he could think of. It's probably the case that if there were something we've left out, that you added it into the model, I guess it would mean the model would fit better, but that's not what we're trying to measure. What we're trying to measure is how good is the crash modification factor that we can develop with the procedure that's been developing. So I don't know, it's a good, if we added new thing, could you expand this to add new things in? Certainly. And so, but then what I'm struggling with is, and then whatever you add in, you can figure out which procedure detects it the best. I guess that's the way I would look at it. So if you added in information on V to I type effects as a characteristic of the roadway, you could then determine which procedure picks out the embedded V to I effects the best. And I'm not sure I've answered your question now.
Yeah. Well, I think maybe partially.
Okay.
I guess what I was getting at is, would you get a better assessment of the CMF if you had more truth embedded in the ARD?
Well, I guess the main goal of the ARD is to figure out which overall statistical method would provide a better, or is more likely to provide a better answer. So this ARD will not necessarily tell you if a particular treatment is more or less effective, or a particular roadway factor is, whether if you change a particular roadway factor, what would be the effect. Here you're looking at, Ezra spent a lot of time trying to be as realistic as possible in terms of putting the different factors. But in the end, the goal is to figure out which method is more likely to provide more reliable CMFs.
Okay. Thank you.
So we have a couple more questions that we'll read here in a second, but just as a reminder that phones are open. If you want to ask a question, please do so over the phone as well. So this question from Georgia: assuming you're using historical data to generate future SV drift from lane crashes, do you have any estimate of the significance on these results of vehicle stability systems and other technologies becoming more common?
Yeah, I think once again, we're kind of into a question of what can we learn from ARD directly about the safety effect of treatments. And again, the concept here is not to learn more about the safety effect for treatments, it's to learn which procedure will pick out those effects better. So it's a hard thing to, it's a hard thing to get, that this, we struggle with this here too. So I'm not, let's see.
I don't know if we answered George's question.
Any estimates of the significance on?
So I'll take a shot at that one. I don't think there's currently not anything in the ARD where there are any estimates being built around what technologies a vehicle may or may not have. And so what you're talking about here is you have to also build in, this would be a kind of a next generation, I think. You'd have to build in, just like Ezra had done for all of the various roadway parameters, you'd have to build in an additional set of parameters now based on the vehicle characteristics and the safety features that a vehicle may or may not have. So it would be another level of complexity, I think, is what you're getting at.
Well, sort of. This is George. I think where I'm going with this is if we don't take into account how crash patterns and trends are changing over time, and probably one of the big drivers in those changes is technology in the vehicles, then is the best outcome of the results that we might get out of this to know what would have happened if we were to have implemented a strategy 10 years ago when the data that we're using was more relevant? How long before the changes in the world are going to make this historical data irrelevant, I guess, is taking the question in a different direction, but I'm just kind of worried that some of the things that happened 10 years ago may not be realistic 10 years from now.
I think it's a very relevant question, George. I think we have that now with our existing data sets and databases and the analysis that we're doing. And it's certainly why I don't think CMFs that we developed 5 years ago versus CMFs we're developing today for the same treatment may have changed because vehicle technology changed. The way we designed the roadway may have changed a little bit. So I think that's very true, and I do think that we have to figure out a way to deal with that. Now, whether that's through ARD, where you could start to build in some of these factors, it's still, back to Srini's point, it's still what you're doing here is you're not trying to come out with an outcome from here. You're just trying to determine what's the best statistical method to apply then to your real world data that you may have. But no, it's a very good point. I think it's something we all in this field have to be concerned about.
Thank you.
And just as a reminder, if you want to call in if you have questions, if you're not connected, it looks like most folks are by phone, but the number is 646-749-3122, 646-749-3122, and the access code is 710-962-597. The access code is 710-962-597. Okay, so there's another question from Kathy. Since observational cross-section studies are being criticized as having too little control, and therefore the results seem to be in question, based on Ezra Hauer's paper published in ResearchGate, then how does the cross-sectional analysis described here relate to that reliability or lack of reliability?
I think that's kind of the bottom line of this ARD is to see, there are certain types of methods that may provide a more reliable CMF compared to other methods. And I want to mention a research study that's being completed right now. That's something that's managed by Dr. Raya Amjadi. As part of the FHWA DCMF A6 contract, we reviewed different methods, the cross-sectional methods that are being done. For example, the traditional regression type approach using propensity scores, matching approach, simultaneous structural equations. Those are all different cross-sectional approaches that they try to make the results more reliable. We just don't know yet if they really are. What we hope is this ARD, if people are able to try these different approaches, we will learn more about if some methods are more reliable than others.
Yeah, I would say, Kathy, you just hit the exact thing that is why this was, Ezra led the development of effort of this back years and years ago, was to see if there was a way to show which cross-sectional analysis techniques are better. And that's what this is designed to do. Okay, next.
So from Nick, seems desirable from statistical model checking basis, but to address underlying issues, what efforts are underway to develop more fundamental causal analysis model based on driver behavior, which should implicitly be flexible to accommodate new technology or transport system changes?
Seems to be that's a kind of almost a larger question that's not just based on the ARD, right? It's a broader question.
I mean, as part of the ARD, Ezra did try to think about what we know about how drivers respond in different situations, and he tried to embed some of those rules in here. I think if I had asked you guys ahead of time to make up a causal rule for how the count of driveways affects the probability of genuine drifting from lane, none of you would have come up with the same thing he came. I'm betting that most of you would not have come up with that same relationship. His relationship has to do with the fact that the driver would be more alert and therefore reduce, whereas I think the normal thinking would have been the number of driveways would have increased the number of somehow single vehicle crashes somehow. So in a way, part of what's built in here and all of these sets of causal rules are at least Dr. Hauer's current thinking about how driver behavior affects certain things. But you're right in the sense that in the future, David mentioned it, or some of you mentioned it for the VDI program, we're going to have to do a lot better job of building causal rules that'll get at the causes of crashes than we have right now. And a lot of this has to do with driver behavior.
Maybe the SHARP 2 NDS data, some of the work being done may contribute to that.
Good point. I guess if you were to say what's the most important database right now for looking at driver behavior and how it affects crashes or near crashes, it would be the SHARP 2 data.
We don't have any more questions right now in the chat pod. Oh, one just came through. Do you see the ARD being used to understand relationships to ped bike crashes?
I mean, this is rural 2-lane roads, so you're looking at a limited number of these crash types being part of the system. But again, the main goal is to understand which statistical method will work.
Yeah, there's nothing. I shouldn't be giving away. I don't think there's nothing in here in terms of a roadway descriptor that has to do with crosswalk design or pedestrian signalization or anything like that. So as it stands, I have to think about, we'd have to think a little more about, does that mean that cross-sectional models looking at pedestrian crashes couldn't be tested with this database or not?
No.
We don't know.
Yeah, I thought I heard you guys talking a lot about vehicular information, so it seemed to me that it was more focused on vehicle types of results as opposed to vehicle-bike, vehicle-ped interactions.
I think one of the things to remember is this is a proof of concept. And trying to determine, can you do this? Can you develop this simulated data set based on what you think are realistic relationships, and then test it, use it for model development, and then be able to grade those models in a way to determine which method is best. If this works the way that we think that it'll work and will provide value to the transportation safety field, then you can think about building in additional scenarios. So that may be additional types of roadways or additional modes that you're talking about here. So So I think that, you're in the very early stages of trying to do something with this simulated data set as a proof of concept, and we'll have to see. We'll see how it unfolds. As Forrest was talking about, this first set of models that are going to be done and graded here in the next couple of weeks.
And again, if you want to ask questions over the phone, the lines are open. I can say the number again, but I think everybody has it. Or if you want to ask any questions to the chat box.
Anna Maria, turning it back over to you then.
Okay, Forrest, and actually to the HSIS team, and also to Doug Harwood and his group, and I want to thank you very much. I want to thank everybody in the audience for being patient with our technical difficulties earlier on. This is great information, and I'm very glad to hear it's been recorded, so we are going to be able to transmit the recording later on. So again, thank you for supporting the series, and thank you for coming out so strongly for